thin material structures, which are thin fluids to some extent, but they still have some solid properties. That's why the name fluid deformable surfaces. So examples are like the cellular cortex in an embryo, or a lipid membrane, or a layer of cells in development, or like a sheet of like muscle fibers or something like that. And I will try to model this by like partial differential equations, and this is work together with Ingo Nitschke. He's a postdoc in my group, and Mike Poorman and Jan Zischke, they are PhD students. Let's frame this from a mechanics point of view. So we are interested in this fluid deformable surfaces are soft materials which have a solid fluid duality. What I mean by that, well, they store elastic energy when stretched or bent, like solid shells, but under in-plane shear, they flow as two-dimensional viscous fluids. So if you never heard about this biological applications for the fluid part, think about a soap bubble, for example, right? And we will model this by so-called surface Navier-Stokes Helfrich type equations. And they are characterized by a tight coupling between tangential flow and shape changes, at least under the presence of curvature. So any shape change contributes to strains, and so must be accompanied by a tangential flow, and vice versa. Any tangential flow on a curved surface leads to shape deformations. So that kind of promises quite rich dynamics for this systems. And framing this in terms of mathematics, well, we are dealing with geometric PDEs. So related to this Helfrich part here, you could say that this is some version of the Willmore flow. But we do this with some internal degrees of freedom. And these internal degrees are, in the simplest setting, our velocity and pressure of the surface Navier-Stokes equations. And then the main part of the talk will be on, well, dropping assumptions on this, on homogeneity and isotropy, and also incorporate activity. Okay, so we are dealing with this free boundary problems, but with internal degrees on the free boundary, and they are all coupled. So we need some framework which couples these 2 degrees of freedom together with the geometry in a way which gives us thermodynamic consistent models. And the powerful way of, or a powerful framework of deriving these systems is the Lagrange-D'Alembert principle. So that's a classical concept from mechanics, but one can extend this in an integral way to our setting. So let's briefly go through this. So what we need is some, well, action potential that's just the time integral of some Lagrangian. And in classical mechanics, that's this Lagrangian is just the kinetic energy minus the potential energy. Now in our setting, we should think about some free energy here. And then on the other side, we need some way to dissipate the energy. We need some energy flux potential. And then we have to specify state variables. So in the simplest setting, that's the parametrization of my surface. And process variables, and in the simplest setting, that would be the velocity. And this notation here, T stands for, well, it's a 1 tensor field in R3, but restricted to the surface. And then we might have Lagrange multipliers to incorporate constraints on the state and process variables. And then this Lagrange-D'Alembert principle says that, well, doing the variation of this action potential with respect to the state variables, here in this weak form in space-time, plus all the corresponding variations with respect to the Lagrange multipliers we get from these constraints on the state variables. This is equal to, that's very demanding to go through this pointer here. Anyhow, this is equal to the time integral of the variational derivative of our flux potential with respect to the process variables and the corresponding Lagrange multipliers. And if we do this and enter some assumptions on the flux potential, then we end up with energy dissipation, and the energy goes down over time, the total energy, kinetic plus free energy. Okay. So what we have in here are all these variational derivatives. So comment on this. So in the simplest setting, we have a free energy which depends only on this parameterization and is only and F is only a scalar quantity. So we can extend this also to vector and tensor fields on the surface, right? But if this is a scalar quantity, it could either depend on our state variable or our process variable. And then we have this total variation with respect to the state variables. We can define this in the obvious way. We get this deformation derivative. But then in addition, as our area element also depends on the parameterization, we have this additional term we have to consider. For the variation with respect to the process variable, well, we have only the first term, as well the area element doesn't depend on the velocity, right? So we get formulas for doing the variations, and now we have to just specify the energies and then compute these variations, and then we can derive our equations. Okay, let's start. We start with the kinetic energy, rho the density, v the velocity, and then the variation with respect to our state variable for this part of the action potential here in space-time. What we get is this term with the material derivative. And then as a free energy, we specify a bending energy, where K is, or kappa is the bending rigidity, H is the mean curvature, and maybe some spontaneous mean curvature. And the variation of this with respect to the state variable, well, we get some stress, and this component-wise surface divergence of the stress gives us a force, and this force acts only in normal direction. And if we write this out, we get this usual form from the variation of the bending energy. Now, besides these energies, we need some flux potential, and here we specify an isotropic viscosity potential. So nu is the viscosity of our surface fluid, and here we have the tangential gradient deformation. And we have to compute now the variation with respect to the process variables, the velocity in our case, do the computation, get again some stress field, and get the force as the surface divergence of the stress field. And then we incorporate a constraint. We want that our surface fluid is inextensible. So we incorporate this by a Lagrange multiplier, that will be the pressure. And now doing the variation with respect to this additional process variable gives us just our constraint. And with respect to the velocity, gives us an additional term which enters our momentum equation. And now, putting everything together and taking into account that our time integral was arbitrary, and we did the variation with respect to all possible variations, we end up with a strong form of the equation we would like to solve. That's this surface Navier-Stokes half-Richt model. It looks like, at least the structure, like classical incompressible Navier-Stokes in 2D or 3D. But here, of course, these operators are the surface operators, and this is an equation on the surface. All this symmetric surface deformation gradient is written here again. And now if we decompose W here into a tangential part and a normal part, we can also rewrite this using this covariant derivatives and the second fundamental form. The material derivative is written here, and the different surface operators I used are written here, and rewriting them again in like tangential and normal component, one nicely sees this coupling between tangential flow and shape deformation, right? So in all these terms, these things are coupled. Now, there are different ways of deriving this equation. Some of them are written down here, and there's also some analysis showing well postness for this system. Now, I would like to show you that one can also numerically solve that. The numerical approach we use is based on surface finite elements. So we have a surface mesh, and this evolves. We use a Lagrangian Eulerian approach, Lagrangian in the sense that we move the grid points in normal direction, Eulerian in the sense that, well, it's Eulerian in tangential direction, and arbitrary in the sense that we also move grid points tangentially to maintain grid regularity. It's an isogeometric approach, so the approximation of my surface mesh is the same as the approximation for the finite elements of our unknowns on it. The Navier-Stokes part is considered with well, P3, P2 Lagrange elements, and Taylor-Hood element. And then we use this Gauss-Weingarten equation to relate the parametrization and the mean curvature and move our parametrization in normal direction. Here we, in addition, incorporate a constraint on the volume, or due to the inextensibility, the area of my surface is anyhow constrained, but in addition, we constrain the enclosed volume by incorporating well, another Lagrange multiplier. And then we start with this bunny and let it evolve, and and then color coding here shows the magnitude of the velocity. And well, I think you nicely see that any shape change induces flow and the other way around. And at the end, as area and volume is conserved, it converges to an equilibrium shape you would also get by minimizing the Helfrich energy under this constraint. And for this, you get to, it's called the Seifert shape, you get to some oblate-like shape. In the meantime, there's also numerical analysis for this approach, and with our approach, we get this optimal convergence rates. Okay. Now let's critically ask what kind of assumptions we made so far. Well, all our material parameters have been constant, right? Density, viscosity, bending rigidity, spontaneous curvature, everything is homogeneous. We assume that the area is constant, that also the enclosed volume is constant, so there's no growth or any exchange with the surrounding medium or so. We only consider like passive systems. Our surface has zero thickness, and well, our numerical approach even allows for self-intersections. So these are, well, definitely oversimplified for these biological problems, or at least the last thing is also very unphysical. So let's try to get rid of this strong assumptions. And let's start with something where, well, it's pretty much known what to do from other fields. Let's start with this global area or constant volume constraint. Well, instead of forcing that we want this inextensibility and say in our constraint that this is zero, we could also say it should be some value, or it should even be some function which depends on time or space. And without any change, that gives us just going to the same procedure, gives us just a new equation with where we can model growth. Right? That's similar to modeling growth in Stokes problems for tumor growth or whatever, where this is used. Or in the same way, we could modify our volume constraint, and instead of saying that the change in volume should be 0, should be something which we prescribed. And then doing this, starting with a sphere and rapidly increasing the area or reducing the volume, leads to such wrinkles. And then due to the viscosity of our fluid surface, these wrinkles heal out. And if we wait long enough, then it still converges to the equilibrium Seifert shape. Okay. The other thing is this possible self-intersection. Also here, it's known what one needs to do. One can avoid this by introducing so-called tangent point energy. So we add just a new free energy, go through the procedure with our variation, and end up with some additional term which needs to be added to our equation. Now, what is this tangent point energy? Sorry, P here is not the pressure, it's just a parameter. It's this double integral over this tangent point radius. And this tangent point radius takes into account the distance between 2 points in R3, but also if the 2 points are close to each other on the surface or not, by considering the normal at this point and the difference. So only these 2 points, which are critical, they actually matter in this energy, or the others don't really contribute. And that if this parameter P is large enough, then theory says that we can avoid self-intersection. However, looking at this, you probably recognize that this is computational quite expensive to realize. There are nice tools in computer graphics which can handle this by introducing P Laplacians and special data structures. However, this all relies on flat triangles to describe the surface, and these P Laplacians, they also modify the evolution. So that's all not meaningful for our biological context. So what we do, we highly parallelize that to deal with that. Okay, let's see if this already allows to at least come closer to some biological problem. So we start with an equilibrium shape and let it grow locally at some point, and I just cut through in the middle to see what happens. Then without this self-avoidance, the area grows, and at some point it leads to this self-intersection. However, with this self-avoidance term, the shape changes, and we get this transition from this discocyte shape to this stomatocyte shape. Right. And we can use the same tools also to model confinement. Like here we have a spherical surface in a spherical confinement. We let it grow locally and have some perturbation at some other point. And then we break the symmetry, the thing grows and leads to this sphere inversion. Well, as a mathematician, I could relate this to gastrulation. So one of the important processes in early development, and the current understanding from biology there is that one needs cell proliferation, so that's we model by local area growth and confined geometries, and this is kind of what we get. Okay. Now next, we want to get rid of this assumption on the homogeneous medium. And the first thing we could do is to say, well, instead of having one medium, let's say we have two different phases with different material properties, maybe two different cell types. So what we need to do is, in addition to what we had derived, we now have an additional state variable phi, that's the order parameter distinguishing between one and the other phase. And a new process variable, that's the material derivative of that. Right, and then we can introduce phase-dependent material parameters. Our bending rigidity, spontaneous curvature, and so on now depend on this phase. And we add an additional potential energy, our Ginzburg-Landau energy, which penalizes changes between the two different phases. Okay, and we need a different flux potential to relax our phi field, and here we use classical Cahn-Hilliard type dynamics. Okay, so we can do this, and now we somehow have a competition between bending and this line energy separating the two phases. And we start with a surface which is already kind of phase separated, and let it evolve. And then it minimizes this overall energy by reducing the bending energy and this line energy. And here it's a situation where both are kind of in the same order, so that's why this complicated coupled evolution. Here also with a volume constraint. Here this volume constraint is switched off, but we start with like different initial configurations. If we are already kind of phase separated and we have a quite strong bending rigidity, then for one phase it would converge to a sphere. However, now due to this additional line energy, the sphere is squeezed together a bit, right? But if the bending energy, the strength of the rigidity goes down and the line energy increases, then we can squeeze this further together, and we get different equilibrium shapes. And might even lead to pinch off, but our numerical method can't handle it. However, if you start with with a more complicated situation then in this situation it will converge to this final equilibrium shape. However, for like a equal competition between line energy and bending energy, we get something like that. And for the case where the line energy dominates, then like for each phase, we can reduce the line by like forming this small bulks which then pinch off. So quite rich dynamics depending on the parameters. Okay. Now, what really matters in this biological applications is the situation where we, in addition, have like some nematic order in this surface, right? Think about like actin fibers or muscle fibers or something like that, and we model them by interpreting this as a liquid crystal in the surface, and describe this by a Landau-Degen type Q tensor field. And it's a Q tensor field means it's a Q tensor which is traceless and symmetric. That's what this Q2 means. Again, it's in R3 but restricted to the surface. Okay. To incorporate this, that would be our new state variable, and well, the time derivative of that would be our new process variable. I want to be general here. That could either be like the material derivative or the Jaumann derivative as the average of the upper and the lower convected derivative. Both do not stretch or do something like that to the Q tensor field. Okay, and then we need a potential or new free energy. It's an elastic energy for our nematic field. Here in a one constant approximation with the elastic parameter L. And then we need to do these variations with respect to the state variable, with respect to the parametrization X here. Again, out of this procedure, we get an elastic force. And we have now our new state variable, it's our Q tensor field, and that gives us the molecular force. Okay. In addition to that, we have a thermotropic energy with parameters A, B, C here in the form for like a 3D liquid crystal energy. And again, we need to do the variation with respect to the state variables, gives us the thermodynamic pressure term entering in the equation and an additional molecular force. Then we need some new dissipation mechanism for our Q tensor field. So that's this immobility potential. And we do need to do the variation with respect to the process variables. That's our time derivative of the Q tensor field and our velocity. And again, gives us some molecular force and this force. And then we modify our our flux potential we started with. So we started with this isotropic viscosity for our fluid. So now we want enigmatic viscosity. So we generalize this thing in some additive form. That's kind of what we had before. And now we have some strengths of anisotropy depending then on U. So it gives us a new form for the flux potential, with this still having this isotropic viscosity and then some strengths of the anisotropy. Again, we have to do the variation with respect to the process variables, and the terms getting more and more complicated. Now I stop here and don't discuss potential constraints and just summarize what we get. It's what we call a surface Beres-Edwards Helfrich model. It's on the surface. Beres-Edwards stays for like a hydrodynamic Ginzburg-Landau type model, and Helfrich stays for the fact that things has bending, right? So the first equation is kind of an extension what we had before. We still have our material time derivative for the velocity. Now we have this additional thermodynamic pressure term here. We still have our bending force, and then we have a more general stress field here, where we now have this nematic viscosity and additional contributions from the Q tensor field. In addition to that, we have on the surface an evolution equation for this Q tensor field. We still have our inextensibility constraint, and these terms describe possible constraints on state and process variables. And the nice thing now is, due to the derivation, we guarantee already thermodynamic consistency of this model. Okay. Now we can take a look at special cases. For example, this isotropic state constraint, so kind of ignoring all the effects of Q. Then we are back to our surface Navier-Stokes Helfrich model. Or saying that we want no flow, kind of an overdamped limit of this equation. We can incorporate this. So what we end up with is a surface Landau-Degen type model. And various people worked on that. It's just a small piece here of the list. Or we can even say that we want a stationary surface, so no normal velocity, that we end up with a surface Beres-Edwards model, and also there various models have been proposed already. Now it's worth to look at some constraints on this Q tensor fields, because there are various models around, or various assumptions around. So far we haven't made any assumption, but a commonly used assumption is to say that it should be surface conforming, and that means that at least one of the eigenvectors should point in normal direction, and the other two should be tangential. Right? Should be aligned with the surface. And then one can even make stronger assumptions and say that the eigenvalue to this eigenvector should be 0. So that we would call flat degenerate. Well, in the first case, we could expand our Q tensor field in R3 into a tangential Q tensor and a normal part. And as it now has consequences, is nicely shown already in 2D. If we assume that our Q tensor, or if we want that our Q tensor is uniaxial, we have to relate this beta and the Q field. And if we do this, this would be the physically or most physical meaningful situation, then the transition from the isotropic to the nematic state by varying our parameters APC and the thermotropic energy leads to a phase transition, and this is first order, and we have phase coexistence. In various models, one sees that beta is assumed to be constant. Doing this leads still to a first order phase transition, but no phase coexistence. And by assuming that beta is 0, so this flat degenerate case, we change the physics, right? So then we have a continuous second order phase transition. So this thing is kind of reflecting the 2D nature of the Q tensor field, and this is still representing like a 3D nature of the Q tensor field. And it also has consequences on the surface. If we assume beta is equal to 0, then our director field, which forms this Q tensor, is not aligned with any curvature or any geometric quantities. But if we enforce beta to be related to our Q, so forcing it to be uniaxial, then actually the director field aligns with principal curvature directions. And you can assume that this has strong consequences on the whole dynamics later on. Okay. Side comment here, well, if we assume the opposite thing, so they're saying that tangentially our Q tensor is 0, so only this beta thing in normal direction plays a role. And then plugging this into our elastic energy actually leads already to all the geometric terms we get from this bending energy. And it gives us a bending rigidity which can be described from this elastic energy and our nematic order beta. This is kind of similar to how Helfrich derived the equation or this energy, but he did it for like an Austrian-Frank energy and without coupling the fluid flow. Okay. Well, so far I showed you always some numerical result for the problem. We are still in the process of testing all this, but what I can do is to look at a special case. Let's assume we have the surface and the Q tensor, but the Q tensor is not allowed to relax. It's kind of frozen in the surface, and it's only transported with this Jaumann time derivative with the flow. Okay. And also the contributions, so it can't relax, and also the contributions to the flow are neglected. So this is what we would like to consider. And we would like to model some morphable sheet, which Antonio De Simono and Marino Arroyo have a patent on, and we work together since some months to model the dynamics of this. Unfortunately, I don't have the sample to show you this, but imagine you have this parallel things which are aligned to each other, and you can slide against each other without any resistance. And in addition, this thing can bend in this direction and in that direction. Right? And then, well, you bend this and form a cylinder. That's like here. And now you twist it in opposite directions, and you apply a force which brings these things closer together. So that essentially forms this shape change here. This is thing we would like to model, and these are some first results. Okay, we are not modeling the exact same situation. We still have a closed surface. We have constant volume inside. What we specify is, it's hard to see here, it's this nematic field on the surface, kind of has this form. And now we let it relax. So we still apply an additional force. So what happens is, due to this nematic viscosity we have, the flow is directed in some direction, which leads to this instability and makes this deformation of the surface. It's a result of this nematic, or the flow on the surface and this nematic viscosity. Okay. Now, what else can we do with our reduced model? I promised to incorporate some active forces. Okay, any biological system has some activity, otherwise would be dead, right? So we need to incorporate some activity, and there are different ways of doing this. One very popular way is to say, well, let's introduce some effective surface tension, so something which depends on mean curvature. It's something which acts in normal direction. And this is often used together with some mechanical feedback. Here are some examples. However, as we have this inextensibility constraint, the surface tension doesn't have any effect on our equation. So this doesn't work. Another way of incorporating active force is popular in active pneumatics and in 2D or in 3D. This has often been done, and it's essentially saying that the divergence of the Q tensor field gives you an active force. So that's what we do in our setting as well, but we have to project the Q tensor to the surface, but the surface divergence of this field gives us a force. Oh, it's a force you can't derive from an energetic principle. Okay. Now, if we assume that our Q tensor field is tangential, and if we further assume that it instantaneously responds to any surface change, so essentially saying that the mobility is infinite in the evolution for Q, then we have this relation between Q and the geometry, and we can kind of decompose Q and express it in geometric quantities. So that's the second fundamental form. That's the projection. E is the Levi-Civita tensor. And we can term this like even part and this odd part in the sense of like odd elasticity. And now if we do this, plug this in here, then do some massage of the terms, we end up with a form which is exactly something which had been proposed before, more on phenomenological grounds. But it's now an even part and an odd part, and it depends on the gradient of the mean curvature. So we introduce a force which depends on changing the mean curvature. And here's an example that's very hard to see. So we start with such a prolate shape. And what is plotted here is this active odd force. So due to this change in mean curvature, this is an opposite direction on both ends. So the active force, oops, sorry for that. So the active force is again going in this opposite direction. And then that leads to, yeah, a shape, oops, sorry. A shape instability. Why is not doing? A shape instability, deforming the whole thing, introducing this flow and so on. And then, well, as an effect of this constant volume and so on, it goes to some shape. Now let's incorporate this in our model, our reduced model from before. Just add this active force. And now I would like to show what is the effect of this nematic viscosity in there. For small nematic viscosity, so that's kind of the initial Q tensor field or the director field shown. With this active force, it's deforming, it's doing something, but it's not very exciting. But with this even increased no, sorry for that. Should start the other video as well. Yeah. With this increased nematic viscosity, we even get some oscillatory motion of the shape. So with the activity and this nematic field, we have lots of freedom to tune some interesting dynamics there. Okay. Some comment on the numerics. It's quite challenging. This Taylor-Hood element doesn't work anymore. The numerics I showed you is done with some Bochev-Dorman stabilization used in some quite odd way with quite high approximation for the pressure. I have no idea why this works, but this is work in progress. And then the last part of the talk, which kind of relates to some of the previous talks, is to think about this thickness of our surface, right? So I always assume thickness is 0 and then assume that it's inextensible and the area is constant. But then, at least for the cell layers, I mean, that's not true. The cells have some thickness, and actually not the area is constant, but the volume is constant. And this height of the cells could change and thereby kind of expand. And that's what we would like to incorporate. So our new state variable is now the height profile on this evolving surface. And our new process variable is, this time derivative, what we call the Trustel time derivative. So until here, it's kind of the material time derivative. And this takes into account the shrinkage or expansion of our surface. And then we now have a different kinetic energy where the height enters here. So like in a shallow water approach, we consider the average velocity within the height as our quantity. And then to regularize this, we introduce a new energy which kind of penalizes changes in height, and we prefer some height h naught, let's say. Right? And then we need some dissipation for the height, and here we use this time derivative. Okay. Now, we start. Also, this is work in progress. We start with a sphere which have different height, and let this relax. So what happens is, due to the different height, this induces tangential flow, that induces shape deformation, and at the end, everything converges to a sphere with constant height. So that brings me to the summary. So what I started with is this Lagrange-D'Alembert principle to derive the equations. We did this for this two-phase flow on the evolving surface and for this Beres-Edwards type model, but it's generally applicable. I briefly mentioned the numerical approach for dealing with this surface Navier-Stokes-Helfrich type model, and then discussed model extensions. So getting rid of this area volume constraint, allowing for changes there, might lead to winkling. We can deal with self-avoidance and use this for the sphere inversion. We introduce some active geometric forces depending on the gradient of the mean curvature and derive them from like active nematic forces. Discuss some surface phase separation and surface nematodynamics, and also briefly introduce this varying thickness. And I guess combining all that together will keep me busy for the next years. With this, I thank you.